In this short but very important video, we're going to talk about something that we're going to continue to interact with throughout this course, which is non-constant acceleration. So we don't always have systems with constant acceleration. You've probably been in a car with somebody who can't quite keep their foot on the gas pedal, as smoothly as they should, and it feels like it's just moving around quite a bit. That is non-constant acceleration. That's what it feels like. And very many things have non-constant acceleration for a variety of reasons. And so because we have our calculus prerequisite, we're able to actually analyze things with non-constant acceleration. So let's just see what that might look like. So we know that our instantaneous velocity v is equal to dx dt, our time rate change of the position, right? So that means that if you have x as a function of t, then you take the derivative with respect to time, with respect to, that's WRT, with respect to time, to get velocity as a function of time. So the non-constant acceleration means that you're going to basically just have a calculus problem on your hand. And if you're going to go from position to velocity, you're going to just take a derivative. Now, on the other hand, we can take the integral of both sides of this, and we end up with the fact that we can get the position would then be equal to the integral of the velocity dt. So in that case, if you have the velocity as a function of time, if you're given that, say, in a problem, then you integrate, and again, with respect to time, oops, I don't know what happened there, in order to get the position as a function of time. When you integrate, you're going to have to look at the initial conditions to get the constants of integration, that plus c that comes out from an indefinite integral, to get our so-called constants of integration. So that's how we move between position and velocity. And then very similarly, we can do this and move in between acceleration and velocity. So acceleration is equal to dv dt. And so what that allows us to say is that we can then get the acceleration as a function of time by taking the derivative of the velocity as a function of time. And we can then integrate both sides, and we can say that velocity as a function of time can be written by the integral of the acceleration with respect to time. And again, when you integrate, that's going to be when you need to use your initial conditions. So if you have a problem and it gives you a function and the acceleration is not constant, then you're going to have to use calculus. The 4 kinematics equations derived previously do not apply, and you will have to use calculus in order to solve your problem. Okay, let me know if you have any questions.